Just your voice and my soul. Just your love.
Okay. Whoa. Shall we get started? Very good. Any questions about logistics? For those of you working really hard, so basically my TAs are basically doing a rolling grading at the granularity of about every day or every half day. So we let 22 people into the course. We expect to let another big block of people into the course. There's still plenty of room, so I would prefer that you take your time and do a good job on the assignment. And the only point of assignment 1 is, for those on the wait list, is just to make sure that everybody's serious about taking the course. And I think things will work out just fine. Any other questions? Yes? Well, I'm not making any guarantees that they'll be on the website, but they are on the website, on the homepage. There's a link from the homepage right now. Right now, they're definitely up. Am I mistaken? I haven't linked them into the detailed page yet. Yeah, usually before the lecture, I only have time to get them up. Okay. All right, so I'd like to start the class by a little bit of review. So these are some of the slides we did not go over last time. I suspect that, hey, everybody, let's go. Everybody ready? Okay, come on. So remember last time we were running code? We were running this little C program on a conventional processor. I gave you all the world's simplest description of a processor, right? It fetches an instruction, it figures out what to do, it decodes the instruction, it executes the instruction, and then it stores the results in some registers, right? Make sense? Okay, so when I said, let's go through this really, really rapid fire, because these are the main ideas from last week. If I said that this was a superscalar processor, what does that mean? And what does that mean in terms of this particular program on the slide right now? We'll start at we'll get us warmed up. It's okay. So in this program, which is single-threaded, has the semantics that it should be run in this order. There may be parallelism across some of the small operations in this program, some of the instructions, right? And a superscalar processor will find it for you, you being the software architect, and try and execute some of those instructions in parallel. And in order to implement that superscalar processor, what I did was I added more ability, twice as much ability to execute instructions in parallel, and I added twice as much ability to actually process the instruction stream to figure out what is out there to run in parallel, right? Single core processor, multiple instructions at once. And I needed to find in certain places in the instruction stream where there was parallelism. And in fact, here's a case where there is not a lot of parallelism, right? Because I have to do that division and then multiply by the sign. In other cases, actually computing the numerator might be parallel with this. Right? So that's what I wanted to show as actual independent instructions. Right? So those two lines of code could be executed in parallel. All right, and there's another situation where there's independent instructions. Okay, so in this program, there's some more parallelism in the program. Or I should really not say parallelism. I should really say there is more work that can be computed independently and therefore would be correct if we wanted to compute it in parallel. Now, where are some examples of that additional parallelism or additional independent work? I'm going to go somewhere else. What other things in this program allow me to exploit? Yeah? Yes? No? No? Okay, there. So this is an independent, like the loop is there is just saying do that for all the inputs. So the loops, the iterations of the loop can be executed in parallel, and one possible implementation of that would be spawning some threads. And in fact, those of you that, I can can hear myself wrestling all over the place. So. No? Okay. So I created 2 threads of control. Those 2 threads of control are now running on 2 completely different non-superscalar processors. I made 2 simpler processors. Is this program faster or slower? Well, yeah, who knows, but define the problem yourself. Let's say that these little cores were almost as fast as the original superscalar core. Sorry? So is now my program, is it getting done faster, more quickly than before? Or like, was this a good idea? Pretty good idea, right? Because I have 2 things I can do at once. I can do different loop iterations at once. Let's go ahead and run them on a parallel core. Now, of course, can I add superscalar capability to my dual core processor? There's no reason I can't do that. And so that can make the individual instruction streams run on both of these cores a little bit faster, right? So now I have a dual core processor that can find instructions for you to run in parallel, right? And we can just kind of scale this up. Here, I now have a quad core processor. I got rid of the superscalar, probably because I was being lazy about drawing boxes. And so now I have a system that can run 4 of these threads in parallel, which means I would have to rewrite that p-threaded program to spawn 4 p-threads, or I might rely on some other programming language or system like ISPC or something like that. And I noticed that I changed my syntax there to just for all independent loop at the top. Now, what else did we observe about this program that will allow us to be even more efficient about executing this? What are other properties that we're like, I see that property, let's exploit that? Let me go somewhere else. Yes? So we noticed that all the parallelism, all the independent work, was all the same loop body. And those loop bodies could be executed using the same instruction stream. So what was our response to that observation? So we decided to go with SIMD execution. We said we're going to design a processor that decodes 1 instruction and then applies that operation to a set, to multiple ALUs. So we modified the processor, and it now looked like this. So now I have a quad-core processor, can run 4 threads at once, and each of those threads, if they want to execute SIMD vector instructions, they can. So in an ideal scenario, versus a single core processor with 1 ALU, how much faster could a program potentially run on this fictitious processor on the board? What is the maximum theoretical speed up here? Yeah. Yeah. 32-ish. How'd you get 32-ish? So 8 different ALUs or 8 different pieces of data, so that's absolutely correct. We could potentially run 32 times faster. All right. So the last thing we talked about in class, or the second to last thing we talked about in class, is most of the class was all about doing arithmetic. But notice down here we're storing the result. And notice at the top we're loading the value x sub I. Those are memory accesses. And we talked about some of the problems or the stalls that can happen when a process has to wait on memory. And so we talked about caches being one solution to solving that problem. And we also talked about an additional solution that used parallelism or independent work in the program, exploited that property to address the memory latency issue. And what was that? What was that? No, you just answered the question. Yeah. Absolutely. When one thread cannot make progress because it is waiting for data to come back from memory, the processor will execute another thread. And what was the term that I used for that in the lecture? Okay, what was the term for that? It was hardware multithreading, and that was a specific instance of interleaving the threads. So it was interleave multithreading. So, and what was the cost of that design decision? It's great because, so first of all, did that technique, did it reduce latency? Or did it hide latency? Hide latency. Memory latency is still there. This is not like a cache that's meant to reduce latency. All the memory latency is still there. We just don't feel the effect of it. We don't take the performance loss because, sorry? You hit it because you're doing something useful when this other thing's going on. In some sense, there's parallelism between the processor and the memory system, and you're leveraging that parallelism as well. Okay. So, and the cost was in fact more state. The need to maintain additional execution context for these additional threads on this processor. And last, I wanted to point out, let's go make this processor superscalar again. And I wanted to point out that if I have a superscalar processor with SIMD execution capability and non-SIMD execution capability, that superscalar processor could be choosing, for example, one SIMD instruction and one regular instruction. So we can make this very, very general as we build up. So here's an example of a quad-core processor, 2 instructions per clock. One of the instructions can be vector. The other one has to be a normal, regular ALU instruction. And there's 2 threads per core. Okay. And if I take this design, and I'm oversimplifying a little bit, and I draw an interconnect and some caches, well, this is starting to look awfully like the capabilities of the quad-core processor in most of our laptops these days. So if you have a Mac Pro, you have something that looks awfully like this. OK, so a little thought experiment to sort of bring up a few issues that you might have not thought about is imagine that we have this processor right here. Let's just say it's a dual-core version of the last slide. So 2 cores, 2-way instruction issue, 2 threads per core. And let's say that I ask you, so someone writes a program that spawns 2 threads. And now, what execution context would you assign those 2 threads to? So there's 4 execution contexts on this processor that can run threads. We want to run an application that has 2 threads. So we need to assign a thread to an execution context so the processor can run it. So it can start fetching and decoding those instructions and run the thread. So we have a choice now. We have 4 options, and we only have 2 threads. What should we do? Yeah. So assign 1 to each core. So on one hand, we could say, let's put 1 thread on this processor on one of these 2 execution contexts. Let's put the other thread on these 2 execution contexts. So why did you choose to do that instead of maybe put them both on the same core? OK. Exactly. So the thing that you're pointing out, and I'll get to your comment in a second, is, first of all, the 2 threads that are sharing this processor are sharing these execution resources. Whereas if you run another thread over here, they're running on a completely different set of execution resources. So to be very, very approximate, if I put both threads on this processor, they both will get half the time. They will run at half the rate. It's like a processor that's half as fast. Whereas if I put the 2 threads on the 2 different cores, they will be able to run using a full complement of resources. Now, someone else had their hand up and probably wanted to add something. Yeah. That's right. Now, can anybody think of a situation where it might be advisable to make the other decision? Yeah. It's absolutely true that I didn't draw caches on here. But if these 2 threads were accessing exactly the same data, you could get a benefit of putting them on the same core because they would hit the same L1. Now, most modern processors, if they're accessing the same data, they're going to hit the same L3 because that's shared across all the cores. But yeah, you could actually get L1 locality if you co-located your threads that were going to touch the same data. Exactly. Now, in practice, I think most of the time you probably want to fill up the machine. But there are some cases where, OK. So here's another question. I just said that there's this application, and that we want to run it on these cores, and that somebody, using this very abstract pronoun, it's not really a pronoun, has to make a decision. But in a real computer, what is who makes that decision? What piece of software is responsible for assigning application threads to physical hardware? And where's the scheduler? Like, is it like an application scheduler, or is it? Yeah, so it's typically, this is a responsibility of the operating system. So those of you taking 410 have done something like this, even though you probably only put threads on one core at a time, I think. I don't know if they have a multi-threaded version, don't they, in 410? OK, so yes, so it is typically the operating system's responsibility to, given all of the applications in the machine, choose which application to run, and in particular, choose which threads to run, and then assign them to execution context. And then just to push this a little bit farther, so we talked about that one. What happened if your program had 5 threads in it? So what happens if you create a 5-threaded program and you tried to run it on this processor? We only have 4 execution slots. Hardware can only run 4 threads at once. And this program has 5 threads. And specifically, you did this in your web proxy because you created a ton of threads, and you were not running it on a high core count processor. You definitely created more threads than execution context. And so what was the operating system doing to resolve that issue? I want to go somewhere else. What was the operating system to resolve? So I have 5 application threads, 4 execution contexts. How did this gap get bridged? Yes? So the operating system is responsible for making sure the machine is shared amongst all of the threads. And I could have asked this question, what if you were running 20 applications on the processor as well? So what is the difference then between a context switch done by the operating system and a context switch when we're switching between these 2 threads? Yeah. So, and that's correct, and those are some of the details, but I want to clarify one thing. So when we're talking about switching between hardware threads, when the hardware is switching between its available 2 threads, the hardware has all of the state to run a thread available in its registers on the chip. So hardware making a decision about which thread of the 2 to schedule onto these resources is happening every single clock tick with very, very low overhead. The only, and the operating system is from time to time at the granularity of milliseconds saying, oh, wait a minute, I need to take all of this state that the processor has to run a thread, I need to rip it off, and I need to put the state for some other application, some other P thread in this application, or maybe some other application onto the processor so that that application can get some time too. So one of these things is done. The version of this that we're going to talk about in this class is happening almost every tick. The version of it that you'll hear about in an operating systems class is actually happening far fewer times per second because it might be hundreds of thousands of cycles to actually take all of this context off the processor and put something new on it. And for those of you that had operating systems, what's the major motivation for a context switch, or what's the major reason to pull something off the processor in OS? Yeah, so there's 2, actually, I should say. So one answer is to give the illusion of concurrency, right, to support concurrent execution of multiple threads. That's exactly what Linux was doing in your proxy. And what's the other big reason to pull a core off a thread? Waiting for memory access? Because we did that yesterday. I/O access. So why would it not make sense for an operating system to pull a thread off of a processor if it took a cache miss? Sorry? Yeah, because servicing the cache miss is on the order of maybe a couple hundred cycles. Actually switching to another thread in software is going to be hundreds of thousands of cycles, probably. Yes? Yes, there's also the starvation issues as well. And we'll get into that a little bit when we talk about synchronization. OK. Any other questions? This is the review from last time. Yes?
The last question was calling 5 threads the question of concurrency rather than
Well, logically, they're all running. All of those P threads are running. They're running concurrently. But they certainly cannot all 5 of them be running in parallel, right? So 4 of them will be running in parallel. And there will be some concurrent execution. Yes, exactly. OK. All right. So Okay, if last class was sort of the most important lecture that you're going to have in the class about how the hardware works, this is probably the most important lecture in the class in terms of how I'd like you to start thinking about software systems. And the biggest thing that I want you to think about, almost in any system that you get your hands on from this point forward, is this distinction between abstraction, what does something mean, and its implementation details, which is how it is implemented. And most of the mistakes in this course actually come from people getting the meaning of something confused with how it's actually implemented. So that's what I'm going to really focus on the next couple of slides. So I'm going to do it by giving the first time we're going to, even though many of you have learned all this, is we're going to talk a little bit about ISPC. And I'm going to ask you some questions about the implementation of ISPC versus the semantics of ISPC. Okay, so ISPC is a very simple programming language. It was an open source project. It is not meant to be an elegant programming language at all. It has some quirks. But what it was meant to do was it was meant to make it much, much easier for you to get the SIMD vector processing capabilities out of the machine. It's meant to be a C-like, low-level language for people that know how to write the intrinsics, the AVX, MMM, 256 stuff that I was talking about last time, but actually don't want to write that stuff. So that's what ISPC was designed for. So if we take this program, I don't want to introduce a new program because this is the same program from last class. If we take this program and we want to write it in ISPC, that program will look something like this. Okay? And what I want to talk about on this slide is what the meaning of this program is. So the code you see here on the left is normal, straight-up C code. This is a C function. It links to a binary in a different object file. And then here is the ISPC code. So when you read normal C code, you're reading this and you're thinking, OK, there's one thread of control. And that thread of control is going to set terms to 5. It's going to malloc some memory. It's going to call this function. We're all very used to thinking about a sequence of instructions that way. OK. So my question to you is, and this is the implementation of this function is implemented in ISPC. So when the C code gets to this statement right here, can someone describe to me how a programmer reading the code on the slide should interpret what happens? Like, what's the meaning of this function call? If this was a normal C program, I would say something like, well, control gets to that function call. Control then enters the function. The function executes sequentially. The function returns, and then control returns back to the instruction pointer right here, and control proceeds. Now, I would claim that that is not the right way to think about the semantics of this function when this function is an ISPC function. So can someone start to tell me what this code even means? Like, if you were to describe to your partner who hasn't started assignment 1 yet, if you were to describe to them, here's a piece of code, let me explain to you what it means because it's in a new language. What do these constructs mean? What would you say? Like, what's going on here at the sign X call? Do you want to give it a shot? It's really hot. It's really hot. OK, so here, I'll start it out for us. So when we enter this function call, and this is an ISPC call, the meaning of that call is that the program will spawn many instances of code that are many instances of the program that are going to run all this code sequentially. So the way to think about it is that when this function gets called, when control enters the body of this loop, there's not just one thread of control anymore. There are, in fact, an entire, and using ISPC's terminology, there's an entire gang of a set of program instances. And it wouldn't be disingenuous for me to say that logically, there are now an entire gang of threads all running the same code. And that when all those threads have completed this code, control returns back to the application. So the way to think about it is if I'm in my normal C code, I have one big arrow. I have one thread of control. When I enter the when the application enters the ISPC function, all of a sudden, there's an entire gang of control. And in this case, I've illustrated a gang size of 8 program instances. And then when those instances complete, and all of them complete, control will return back to the single-threaded original C code. OK. Now let's look at what this program does. So this program is being run by one thread. This program is being run by 8 instances. So can someone tell me, and the only changes to C in the ISPC syntax are actually all there in red. So first of all, do you agree or disagree that this program actually is correct and that it computes the sign of all of the numbers in the input array? And for someone who thinks it's correct, can you explain to me why it is correct? Yeah. But I wouldn't say SIMD because I'm not talking about implementation at all at this point. I could, presumably, and there's some reasons why this is actually not true, but for the sake of this lecture, it's perfectly fine if you wanted to think about the implementation of that function call as spawning 8 pthreads. Right? So I don't want to say the word pthread. I don't want to say the word SIMD. I'm not going to talk at all about how this is implemented. I just want you, and I think you know, can you explain to me why this logically computes all of the values that we need? Yep. So let's just say, so we're assuming that every instance gets the same parameters, and that there's a built-in variable, 2 built-in variables, that any instance, any sequence of sequential code here can access. One of those variables tells you the number 8, the number of instances that actually got launched. That is program count. And another variable will take on a different value in every instance, which is essentially a thread ID or an instance ID. And that is program index. Okay. So given that, how do these 8 instances compute all of the elements of the array? Come back in 1 second. Want to finish up where we were? So instant 0 computes what iterations of the loop? Right, so 0, 8, 16, and so on and so on. And instance 1 will compute iteration 1, 9, 17, stuff like that, right? So can everybody see how, logically, this program does all of the work that my original C program does? Gets the exact same answer. You agree or disagree? Agree, OK, yes. Sure, yeah, actually, I didn't. I could add some extra logic in there to get that. But yeah, you're absolutely right. This code is written assuming that program count divides n. Yes. Let's see. Yes, they will just early out of the loop, and you'll be fine, actually, I think. Yep. I believe that is true. Yeah, I think you're right. Yep, exactly. Good catch. OK, so is everybody with me at this point? OK, so mentally, how I think about that program is I have a single thread of control. I call this function. Now, 8 different logical instances or logical threads are running that function. They all do different work because of the way I wrote the program. And then when they all complete, when they all return from that function, control just keeps going from the original C program. OK. And we talked a little bit about some of the keywords. Program count, the number of instances. Program index, the current ID of any one of those instances. There's an extra keyword. It's actually a type modifier here, which all of these variables, you can think about there being a copy of all the variables for every one of the instances, right? Because they're different threads. There is a detail here where if you mark a variable uniform, you're actually telling the compiler that this variable has the same value in all of the instances. And there's some implementation details for why that's there. But that's not really something you need to think too much about now. Okay. All right, and so we talked about how all the program instances do the various work. So if these are all of the iterations of the loop, instance 0, if there are 4 instances in this case, I drew a smaller group. We'll do 0, 4, 8, 12, 16. Instance 1, we'll do 1, 5, 9, 13, and so on and so on. Okay. Yes? The number of instances is actually a compile time flag to this program. So if you actually look in the makefile of assignment 1, we have actually set the number of instances in most of the cases to 4 for SIMD instructions. The machines support 8-wide AVX instructions. So there's another flag you can change, and we encourage you to try it out, where you can change it to 8 or even larger. So in ISPC, that is a compile time decision. Now, here's an interesting question. Who can tell me how any of this stuff is implemented? There's actually a reason why it's a compile time thing. Because if this was if I was spawning 4 pthreads in this case, you would think it would almost be a function call that said run sin x comma 4 or something like that. Right? But now I want to okay, so now everybody understands what the program does. Now let's think about how the ISPC compiler is actually going to implement things. So does anybody have a sense of how this thing gets implemented? Like if you read the ISPC manual, it tells you this is how the program works. Good. Okay, so the actual implementation of ISPC is that even though the program says, hey, you need to run this whole gang of instances, and I don't care when you run them, the implementation is going to be, oh, if you want 8 instances, I'm going to take every instruction in that program and translate it into an 8-wide AVX SIMD instruction. So that even though logically, we can think about this as 8 different threads of control, it will be implemented as a single instruction sequence that uses vector instructions and is run on a vector processor, much like we talked about last time, or much like what I ask you to do in part 2 of assignment 1. So part 2 of assignment 1, you are manually implementing what the ISPC compiler does under the hood. So the implementation is via SIMD instructions. And that kind of makes sense on why the gang size needs to be chosen at compile time, right? Because the gang size tells me, am I using AVX or SSE and so on and so on. And in fact, the actual details, if you look into a little bit more of the output, is ISPC will take that program, it will compile it to a .o, just to a library, which is a single-threaded library with vector instructions in it. And it emits a .h, which is just the signature of this function call. So this is just a regular C function call that happens to call a C function that is single-threaded but full of vector instructions, full of SIMD vector instructions. Okay. So this is the same code as before. And I changed, no, sorry, it's not. I actually changed the code. So can somebody tell me how this code here is different from the previous code? In the previous code, every program instance was responsible for iteration imod program instance. So the first program instance did 0, 4, 8. The next one did 1, 5, 9. I changed the assignment in this code. So take a look at this code for a second. Everybody take like a minute or something like that. You look over with your friend or your partner and see if you can figure out what it's doing. how have I changed, just take like 30 seconds, how have I changed the program to assign work differently to program instances? So take 30 seconds and make sure that everybody's following. Okay, so who wants to help me out? How is this work assigned to the program instances? You had your hand up before. I'll give you the opportunity. So you're saying instance 0 is now responsible for iteration 0, 1, 2, 3, or basically n divided by number of instances. That's the chunk size. Exactly. So the relationship now is instance 0 will take on these iterations of the loop. Instance 1 will take on these iterations of the loop, and so on and so on. So here's my first question. Is this program also correct? Does it compute the same thing as the last program? Absolutely. Now, here's a little bit more complex question that has to do with the implementation. Which implementation do you actually think runs better? Now, I haven't given you enough information to probably answer this question, but I'm curious. Yeah. OK, so your answer here is instance 0 touches a bunch of elements right next to each other. Good spatial locality. Instance 0 touches a full cache line of data. You're thinking about Cache Lab. Makes a lot of sense. OK, that's a good line of reasoning. Does anybody else want to add anything to it? Yeah. I think this performs worse. OK. OK, so let me talk a little bit about what you just described. So let's go ahead and diagram this thing out. And the columns of my diagram are what every instance is doing. The rows in my diagram is like time. And let's just think about time not as clocks, but let's think about time as iterations of the loop. So, or values of I, right? Because in this case, if I go back to the code, yeah, values of I. OK. So if you think about what's going on now, if the implementation is via SIMD instructions, all four, or in this case 4, instances are loading consecutive elements from memory at the same time. So your reasoning about cache locality was very correct, but it actually, the conclusion is the exact opposite of what you were thinking, is that if I want to hit the same cache line all at the same time, I actually give different instances adjacent values so that I hit the memory system with one big contiguous block of requests at once. And that would be somebody referred to a vector load instruction. Here is in SSE, that would be the packed single precision load instruction, load packed single, which says grab these 4 consecutive floating point values from memory and bring them all in at once. And the equivalent here is the store down at the bottom. Now let's look at what happens in the second. Yeah, go ahead. So ISPC only supports various gang sizes that it knows how to code generate for. And it will know how to code generate for any integer multiple of an actual SIMD instruction. Yep. So for example, if you tell ISPC to use AVX and generate a gang of 16, that typically is usually your best performance. Because you use the big fancy AVX instructions, And okay, just digging deeper a little bit, do you know how it implements a gang of 16 on an 8-wide vector machine? Yeah, for every op, you just emit 2 instructions with just different addresses, right? And they're 2 different, completely independent ops because the first instruction will operate on the first 8 elements, and the next instruction will operate on the next 8 elements. So you have 0 data dependencies. So you actually give the superscalar execution engine a lot of room to work with, and it actually runs much faster. Okay, so now let's look at the alternative. This is the second program I showed you, where now every instance back to back to back loads consecutive elements, right? So this is the blocked version, the second version. And now look at what happens at any moment in time. And at any moment in time, that SIMD load instruction needs to load separated addresses in the address space. And that's actually a much less efficient thing to do for a variety of reasons. This is often called a gather in SIMD processing. So the instruction goes from this load packed single precision to, in fact, gather from these indices. And you can imagine that can be a tough operation because, for example, if n was really large here, this gather would be elements separated by 1,000,000. And so every single element of the vector would miss the cache. And so you'd actually take 4 cache misses on that single instruction. OK. Cool. Yeah, so that's now a gather. Now, in ISPC, you'll see in the code that I give you, and also in most of the code that you prefer to write, I actually did not do this manual interleave loop thing. I actually, in the code, we often use this primitive for each. And so for each is actually, it's weird. And this is where I think ISPC gets a little bit ugly. But for each is basically saying, here are n iterations of a loop. Take the loop body and assign them to instances in the gang however you please, ISPC. I don't care. Right? So this is a for loop that's actually being run per gang and not a for loop that's being run per instance. See the difference? So if I'm running a gang with a for each in it, this is basically just saying, this gang will perform all n of these iterations. Compiler, you handle the assignment of iterations to actual instances. Now, what implementation do you think ISPC actually uses? It was the first program I had up on the board, because that's a very efficient program. So this is basically just syntactic sugar, a much prettier version of the code that I had up on the board. But what's the difference here between this program and the first program I had on the board? Is the difference in semantics, or is the difference in implementation? It's in semantics. So what are the semantics of this program? Sorry? Well, if you read this program, well, all of the programs look like a single-threaded one. But if you read this program says, here are n iterations. They are all independent. And that's all it says. Right? And the compiler uses the information they're all independent to assign them in parallel to the various instances that the compiler knows are running in parallel. The implementation of that assignment, to the best of my knowledge, is that the underlying compiler will perform the interleaved assignment that we talked about, because that is a very efficient one when you're mapping to SIMD instructions. Question? What is where it somewhere doesn't belong? Let's see. Yeah, so basically, if you violate the contract, does the compiler check that you violated the contract? And the answer is no. Right? So in a much more strongly typed language or a more pure functional language, the compiler might be able to confirm that your expectations have not been violated. This is a low-level C language, and there's no attempt to violate or to verify that you have correctness. Okay. Yeah. Yes. That's right.
So it could so happen that
Correct. Well, first of all, it has to load a cache line and only uses one piece of data out of it. So let's look at this. So imagine that this is a much bigger, a much larger gang size, for example. Let's say it's a gang size 16 or something like that. So then I'm going to load one element from every cache line. So I have the worst possible spatial locality, because this would be 0, 16, 32, 48. So every cache line that gets loaded, I'm only going to touch one element in it. I guess technically I'll touch the next element in the next cache line. That's true. So in both cases, actually, I'm going to get pretty good cache locality. I think the challenge is that the packed load is turned into a gather, which can be a much more expensive, well, just is a much more expensive instruction to implement. We can talk more about that, actually. It would be an interesting experiment to write both of those and benchmark these and see what you get. Yes? You could. I mean, if you're in bad shape and you have a low associativity L1, but in general these days, L1 associativity is pretty high. It's like 8 or 16, so you're probably not going to crash. Yeah. I mean, the other thing is that since it is a gather, even if all these subsequent ones are hits because the cache lines have all been loaded into cache, the processor's still got to sort out the indexes and stuff like that. It doesn't know that they're all consecutive from the previous one. So it's just a harder instruction to implement the processor. It will be significantly slower. So you're asking me how is this implemented? Right, I want to be very clear about that. It'll certainly be implemented. Let's say if our gang size is the same size as the SIMD width. Vector lane 0 will probably do all of the work of instance 0. Yes. But you're asking about an implementation detail of the compiler at this point. And you should think about this when you're doing part 2 of assignment 1, how you decided to do it. I imagine that almost all of you decided to put vector lane 0 as iteration 0 when you're parallelizing the program. OK, so just to review here, is that the semantics of ISPC are you write a single program that runs on multiple pieces of data. Bunch of 8 instances are running, 4 instances are running potentially on different data. The implementation is that the compiler will compile that program into a sequence of SIMD instructions. And that I'll let you refer to the details of ISPC to kind of learn sort of the nuances of some of the semantics. So here's an example, very related to a question I just got asked. Here's an ISPC sum reduction, or a potential sum reduction. So is this a correct program or not? If you go back to the question that you asked me just a second ago, my claim is that this is an invalid ISPC program. And why is this an invalid ISPC program? OK, so you're claiming that there's a race condition here. And what is that race? Here, OK. So what is the race? So sum is a single shared value. Uniform, there's one value of uniform per thread. Per gang, excuse me. And that all of these loop iterations, the contract for each is that they can be executed in parallel if the compiler wants to. But now I have a plus equals. I have a read, modify, write into a single shared variable that's not protected by a lock or anything like that. So the output of this program is completely non-deterministic. We do not know what the actual output is. So sum is of type uniform float. There's one copy for all program instances. And all the programming instances are writing into a single value. Now, in this particular case, this is actually a write to a uniform from a variable, and this will type error. So the compiler will be able to catch this one for you. Sorry? Oh, fair enough, yes. OK, so here is a correct ISPC solution. So imagine I gave you a magical function, which they do, which adds up across all of the instances. So this function is called by all of the instances and returns a value that is unique for the entire gang. So can somebody explain to me how this program works in terms of what the instances do? And if you can explain how this program works in terms of what the instances do, you're starting to have a pretty good command of ISPC. Let me go to the back. Yeah. Uh-huh. Good. So let's say I have a gang of size 4 instances. I have a for each loop, which says for every element, assign this iteration of the loop to one of the instances. And every instance has a local temporary variable called partial. And I called it partial because it's like a partial sum. So when the for each is executing, all of the various instances are getting some subset of the iterations. They are accumulating their partial sum into their local variable partial. And at the end of the for each loop, I have 4 different partial sums, one for each of the program instances. And then I need to one of these operations that actually communicates across the instances. And there's a library of functions that help you do that in order to take those partial sums into the final per gang sum, which is then returned back to C code. So this is the proper way to do a reduction in ISPC. In fact, if you might find this interesting later, is if I actually wrote the compiled code by hand, it would look something like this, which is basically loop, executing vector instructions that do an element-wise add. Every element of the array is now a partial sum, and then at some point I just add up the 8 elements of the vector. Yeah. So say that again. I just declared float partial. So there is a difference, right? So one of them I said this is per gang, and the other one I said this is per instance. Mm-hmm. So the type signature of reduce add is float to uniform float. Okay? Mm-hmm. Okay. And then I'm going to leave to you guys on assignment 1 a little bit of time to kind of figure out if launching an ISPC function is like executing in SIMD. There's another construct in ISPC to launch threads onto different cores, which all may run in SIMD. And I'll leave that for the assignment. OK. So any questions about that little ISPC tutorial? Yeah. Uh-huh. All program instances are being executed on the same core in all of these examples. I have not referred to any code yet that runs on multiple cores. So I want to clear that one up first. OK, so what's your question on this? OK. So let's go here. Partial is just a local variable of every instance, right? We know that the semantics of for each are that all of the n iterations need to be run, and each of the instances will run some of them. And they will run, any one instance will run its set of iterations sequentially because it's one instance. It's only one thread of control. So when the for each is done, that means that all of the instances have run whatever iterations they're supposed to run, and they have executed the body of the loop. So what they would have done is they would have loaded xi, and they would have added its value into their local variable called partial. I don't know what that means. Yes? Yes? That's all it's doing, yeah, in this case. Uh-huh. Yeah. Sure, go for it.
So in the first class we had 4 students trying to add something all at once.
Yes.
Now, if we had a person who kept the counter, and like say one person would tell them, okay, the new sum is this,
Uh-huh.
what happens then? The fifth person tells one of the others what the current count is, and the other person adds it and brings it back.
I like the analogy. I just don't want to add the 5th person. Let's do it this way. Hey, everybody. So the right analogy to how the correct version of this code works would be is if every single individual, if the 4 people we had up here added up all their own numbers all the way until they were done, and then the reduce add function at the very end is all 4 of those people just adding up those 4 numbers together. So I would prefer not to say there's a 5th person. I would prefer to say that the reduce add is this prearrangement that they had all figured out on how to add up their numbers. I think that would be a better analogy. Yes. And it's just a built into the language is one way to think about it. Okay. So shall we move on? Okay, one more question, then I want to move on. Okay. Okay, so up there at the top? Yeah, here's an interesting question, is how many times is reduce add called? So you can think, I think the right way to think about it is that anything that's uniform is called once. Okay? Or you can think about it as all of the instances calling reduce add, and it responds once. Because it returns, so if we want to think about this in terms of types, the type signature of this function is per instance float to uniform float. Right? It's per instance floating point value summed up to a uniform value, which then all the instances can access. I don't do it in this code, but all the instances could access that. And notice that all the inputs and arguments to the ISPC function are uniform, because they needed to come from C code and get back to C code. Yeah, those are just local variables. I mean, so for the most part, you can just think about an ISPC instance as a thread. It's just a thread local variable. Now, it's a little bit disingenuous to call it a thread when we start thinking about the implementation of it. But logically, for almost all practical purposes, it's a thread of control. Okay, last question for real. Yeah. You could, but ISPC doesn't give you any. So if they wanted to allow you to synchronize across the instances, they would have given you them. But there's a pretty strong reason why they do not and will not ever give you any. And do you know why? Let's go back to the implementation. Yes, but really what it is that these are not actually, that's why I'm saying it's like you can think about them as threads, but really there's choices in this language that really indicate that the designer said this is never going to be implemented as threads. And one of them is we have all these variables in lockstep. And actually to throw a lock or a semaphore in there, these are not arbitrary threads that are doing very different things. These are logical sequences of control that are absolutely going to stay in sync. And so kind of the only operations that make sense are these reductions and things like that. So they give you a library of all the appropriate ones and the ones that can be implemented efficiently. Like, for example, this could be implemented, that reduce add could be implemented as this for loop that I have here. For I equals 0, add up just all the elements of the array. But because it's a reduce add, if there happened to be an instruction like a dot product that adds, in a single cycle adds them all up, the compiler could generate that instruction. Okay. So in the last half, kind of the lecture, I'd like to start moving towards other ways to think about programs. So ISPC gives you one way to think about programs, and it's a very, very SIMD heavy way to think about programs. And I want to think about some other ways to think about parallel programs. And I want you to keep in mind when you review this lecture, when you write your comments, think about what do each of these programming systems, how do they encourage you to think about what the program means versus how do they actually implement it under the hood? So when I describe to you, let's think about an ISPC program. I say you have one thread of control. When you call an ISPC function, there's now 8 instances running. And then they all kind of join back together. And then there's one instance running again. So I never said anything about the implementation of SIMD. And in fact, if you start thinking about SIMD, sometimes it actually confuses you more. And we're going to do that again today. So there's going to be a lot of different layers here, right? For example, the hardware presents some abstractions like instructions, execution contexts. The operating system presents applications, new sets of abstractions, and so on and so on and so on. So let me give you one example here. So imagine you're programming with pthreads. Well, when you're programming with pthreads, what does the application programmer think about? The application programmer is like, well, I've got these logical threads of control, and they're running concurrently, and I don't even really think about whether or not they're running in parallel necessarily. I think about them running concurrently. They might be running in parallel. And so that's sort of what we think about. We all kind of know at this point what a thread is. And how do we actually create the thread? Well, you might call pthread create. That's the architecture presented to you. And then there's an implementation of what a pthread create does. For example, somebody's got to create that thread stack. Somebody's got to create some local variables. There's some implementation details of that. Those implementation details probably go all the way down to creating an OS-level thread to mimic that application-level thread. And then the hardware has instructions for, first of all, creating, or not creating, but mapping those threads to execution contexts, as well as doing the logic of the thread. Those are what instructions do. So there's a whole bunch of different pieces of hardware and software that work together to kind of implement this idea of a concurrent thread. So interestingly, like ISPC has its own set of a system stack, right? So in ISPC, I have this idea called a gang, a program instance. Well, I don't make a pthread call to implement a program instance. This the ISPC compiler goes from this logical notion of these independent instances all the way bypassing the operating system straight to vector instructions. So the implementation of this logical thread of control doesn't use the operating system or pthreads at all. Okay, so I want to close up by, well, not close, but the back half of the lecture here is going to be about 3 different ways to think about parallel programs. And the first one is the one that you already completely think about when you think about parallel programs. And that is, I have multiple threads of control. I have an address space where there are variables. And those threads of control can read and write from those shared variables. That's exactly what you did in 5.13 or 2.13. It's exactly what you'll do in a lot of the programming systems in this course. So for example, I might have 2 threads. Thread 1 creates a thread 2. Thread 1 and thread 2 both read or write from some shared variable x, which I have here. In this case, thread 1 stores to x. Thread 2 waits until x is not 0 anymore, assuming that, yeah, thread x was initialized to 0. And then when x, thread 2 loads the value of x and ultimately prints it once it's non-zero anymore. Simple pthreaded code that uses reading and writing to shared variables. If we have shared variables, your code will need to synchronize access to those variables. Otherwise, we could get into race conditions. And you had one race condition in your proxy in 2.13, and you'll have many more race conditions in this class. So here's an example of this thread wanted to update this counter to run x++. This other thread also wanted to update this counter. And they protected it with a lock. And this is very much probably like your proxy assignment. So why did you throw these locks around shared variables in the proxy? I've heard the term race condition, but really I don't care about race conditions because I want to know what bad things can happen. Or in other words, how can the program be incorrect in this scenario? And in this example, what if x was 0 and 2 threads went to increment x? What bad things can happen? Load x into a register. Could write 1 back to the memory. So like both threads can read the value 0. Now we have 2 copies of x in the 2 different processor registers. Both threads can think about, they're just doing the right thing. They're incrementing x. They both increment to 1. And they're like, oh, I should put the value back in memory. So if anybody else wants to increment x, they can do that, right? So but then they both put the value 1 back in memory. And the result now is not correct. So in this case, I protected that shared variable with a lock. And so, so the shared address space model, it's sort of like all the variables are up on some bulletin board, and all the threads are people. And in order to communicate, you go up to the bulletin board and you change the value of some flyer. That is a reasonable analogy for a shared memory programming model. And that machines that you run on have to support this style of programming. So for example, any modern multi-core laptop is a shared memory system. There's one memory system, and there are multiple cores hooked up to it. So here I'm showing you an example of a 4-core processor with memory over here, and then there's some network that routes all of these requests for reads and writes for data over to the memory. And we'll have a whole lecture in this class on different ways to build this network so it can be really fast. So we might connect every processor to every other processor. We might have a shared bus. And these networks, like some of the most interesting stuff in processor design these days is actually in how to design these networks so that all these processors can communicate very quickly. So here are some examples of multi-core processors. If you look really closely, you can kind of see like this is the shared cache, but there's a network that's the communication substrate between all those cores. An interesting other thing, so here's a fairly recent, I guess it's a little old now, it's an 8-core chip, and it has a crossbar that connects every single processor to every other one. And that crossbar is actually as big as any of the cores on the chip. So the amount of area and the cost for a high performance network is actually quite high in most modern processors. So in all of these designs, I was sort of alluding to all of the processors can access the same memory. And in most modern processors these days, like for example, if you have a dual core processor and the dual core processor, sorry, the dual socket, not a dual core processor, but a dual socket system, where they have 2 processors and you plunk one down here and you plunk down one here. In the motherboard, the memory system often has different channels out to different memories. So usually if you have a dual socket system, you'll have much higher memory bandwidth. And every processor can talk to any memory address. But if a core 0 loads a value that happens to be a physical address over there, it actually has to go out through the memory controller of the other core. So the cost, the latency of memory is actually different depending on what the value of the address is. And so if you're really beginning to optimize code, you actually start optimizing for those kinds of things more so than just cache hits. And as the machines get bigger and bigger, this effect can be quite interesting. Is that, again, here's an example of a shared memory system. And the memory is just partitioned across all the machines. So load X might be quick if X is stored in a local memory. And load X might be really expensive if X is stored somewhere far away. And so here's an example of a machine that we used to run assignments on. It's old now, so we don't want to make you run assignments on it. But it was at the Pittsburgh Supercomputing Center. And it had 4,000 cores. And those 4,000 cores shared the same address space. You could just say load address X from any core, and it would go get the data for you. So you can imagine the difference in the access time cost between an L1 cache hit on the current core and a memory access that happened to go from like the processor in the top left corner here to the processor in the top right, in the right corner there. It's like about 1,000x difference in a DRAM hit close to me versus a DRAM hit far away, not even counting the cache differences. Okay, so the shared memory way of programming is basically I am used to single-threaded programming, and I'm just going to make a baby step to having multiple threads. And I'm going to punt basically to the hardware manufacturer the ability to get data from one processor over to the other processor. And I will pay a lot of money for me to punt that problem to them. Okay, so how many of you have done distributed systems in this class? How many people have ever made an HTTP request? Okay, everybody's at least made an HTTP request, right? So would you say that all of the machines in the world share the same address space? At least they say memory address space. You could say that URI is kind of uniformly set these things, but I wouldn't say that. So as we get to bigger and bigger machines, we start thinking about processors with their own memory, and that communication between processors needs to be through explicit messages. So if I want to hit Google, I send Google a packet, right? I send them a message saying, I would like this data, give me the data back. If I have a cluster of machines and I'm trying to write a program on a cluster, and I say load address 0x43, I don't expect that 0x43 will be serviced by a machine on the other side of the machine room. So the message passing model of communication is actually you need to mentally think about each of your threads has its own private data, and that if any threads need to communicate with any other threads, they will do so by explicitly sending a message. So if we're going to communicate, I'm going to say, OK, here, I'm going to send you this message, and it has the ID foo. So send foo to the back of the room. And I would expect another thread to say, I expect to receive foo from Kayvon. And these things are going to get matched up. So a thread here might make a function call, send the contents of the variable x to processor 2, and let's give it an ID so we can identify the message. And processor 2 might be over here saying, hey, I expect to receive a message from processor 1. It has this ID, and when I get it, I want to store it in the local variable y. How would this communication have worked if this was a shared address-based system? What do you mean by a mailbox? OK. So that sounds a lot more, in some sense, like a message, actually, than a shared address-based system. I think there's an even simpler solution. If we are both two threads, two processors that share an address space, and I want to communicate information to you, what could I do? What's the simplest thing I could do? We could just agree on an address, a variable, and I can write to that variable, and you can read from that variable. And we may need to synchronize, but we could just read and write to shared variables. Messaging, there are no shared variables. You have your own variables, I have my own variables, and if I want to get information to you, I send you an explicit message. Or I could use like a mailboxing primitive in an operating system like that. But I would almost think about that as more explicit communication. Yeah. A lockbox in a clubhouse. Yeah, sure. OK, I get it. I get it. Yes. So here's a question, actually. Do you need locks in a message passing system? No, people are shaking their heads. So why don't we need any locks at all in a message passing system? OK, it is. Well, it's not. First of all, it's not necessarily asynchronous. That's an implementation detail. But let's keep going with that. So let's say it was synchronous. I still assert that you don't need locks in a message passing system. Well, keep it moving. Yeah, why? Because there are only private variables in a message passing system. I have my variables. I have my address space. You have your address space. If we're going to communicate, we'll send messages. But I don't have any ability to touch your addresses, because that's an address space. And I have my own address space. Yeah. There are many communication challenges. And I'm not saying that it's easy. But the synchronization, the locking, has now turned into a problem of setting up a protocol of sending messages. And you'll definitely see that in an assignment going forward. So as these machines get bigger, and it becomes essentially impossible or very, very inefficient to make an address space that spans tens of thousands of processors, you'll see machines, like some of the largest machines in the world, like early supercomputers from IBM, or actually just clusters of workstations in any modern data center. The operating system provides an address space for every process. But if I want to use a bunch of processes across a bunch of machines to write a big parallel program, they're sending messages. They're sending messages. And for example, here's a cluster we have available for our own use. It's called late days. And it has 16 nodes. There's just 16 machines. They're connected via Ethernet. Some of those machines have GPUs, some of them have Xeon Phis. In general, there's a lot of compute. It's kind of funny. It actually would have been the #2 machine in the world in only 11 years ago. It's not that impressive a machine today, but it would have been the #2 machine in the world in 2005, I believe. But if you want to write a program that uses all of these machines, you can't just load and store to shared variables. You're going to have to send messages because the hardware only supports communication via messages. Okay, so I think it's 2:45 and it's really, really hot in here. So I'm thinking that rather than try and I'll just pick this up on Wednesday because this is getting kind of insane. So, but hold on. First of all, does any questions I can answer? We had an office hours today. I saw a lot of people there. I like that. I answered a few questions. There's a lot of extra material I don't talk about in lecture that other students have asked me about in previous years. I think we can ratchet up the comments on the website to start addressing some of this stuff now, because now you have everything you need for assignment 1, for sure.